and I like to discuss a topic that has been on my hello. Yeah, I see that's my cameras. Yeah, well, okay, I'm live now. Okay, I like to discuss a topic that is puzzled me for quite a while, and which is a topic in science, in quantum mechanical science. And many scientists they use the term of wave function collapse. And I've been thinking over that subject for quite some time, for many years. And the thing is, does a wave function indeed collapse, yes or no? That's I think it's the Copenhagen interpretation that the wave function collapses. And but what really happens, and is the term collapsing, is that a correct term? Well, to be honest, I don't think so. It's a correct term. I think that gives a misrepresentation terminology wise. What a word! Compared to what really happens. And I try to describe what happens in what is known to be a wave function collapse. I don't think it collapses. I mean, we know that we can describe a wave function as a formula, a mathematical formula. Well, okay. The thing is that what happens if you have a wave function, if you have a particle flying through the air, flying through the space, some area of space, it's a spread out phenomenon, and because of what we in the end see, for example, in the two-slit experiment from Young, we see that in the end a particle is hitting a screen and leaves behind a fluorescent mark or whatever. They leave behind a certain kind of mark. And many scientists, scientific-oriented people know the picture. You have a gun, a particle gun, and two slits, and behind that a screen in which an interference pattern emerges after a while, especially if you fire particle after particle, then that interference pattern builds up. We know that. That's common knowledge in science, within quantum mechanical science. But what we do not know, and what we do not seem to understand, is first the measure of a wave function being spread out in the case that a particle is flying separate from all kinds of instruments, including the particle gun, including the detection instruments, etc. So when a particle is flying on itself through space, from left to right, or from right to left, or whatever, then it has a measure of spread outness. It's being spread out as a wave in space-time. And it can interact with itself. That's the nice thing about it. That gives the so-called weird phenomenon that we see in quantum mechanics. So we think it's weird, but it's actually not. It is just being a wave. That's why the name wave function. Okay, but a wave function can change, and that is exactly what happens. It does not collapse. It changes, it merges, it alters. So a wave function 1 alters to a wave function 2 with a different description and a different wavelength, a deBroglie wavelength. Since each particle with a given speed, with a given mass, has some kind of deBroglie wavelength. Well, and that's basically what happens. It changes from one type of wavelength to another. And if you speed up, for example, an electron by speeding it up in a gun, then the wave function becomes smaller and smaller and smaller the more you accelerate it. So the mathematical description of a wave function of an electron, of an being sped up electron, the wave function shrinks. Yeah? So the wave function becomes smaller because the speed is increasing. And by the formula lambda divided by m times v, h divided by n times v, that's the wavelength, the deBroglie wavelength of a particle. Then the higher the speed, the mass is fixed, as long as, especially as long as you are in non-relativistic speeds, then the mass is kind of fixed. It stays pretty the same. If you look at the graph of the relativistic masses, then it only increases very high if you go to the light speeds. If you look at that graph, because of the gamma factor. The thing is that the wavelength decreases if the speed goes up from that particle. But suppose that you have a particle that doesn't travel that hard, but let's say a millimeter per second or so, or a millimeter per whatever kind of time per minute. So the speed is low. Then that particle has a very spread out wave function. Now, what happens? If it interacts as a wave with the two slits, but does not collide with the two slits and passes through one of each, through both of the slits, and it does not physically interact with it, then it continues behind the two slits and it interacts with itself. It interferes with itself, and we get the known double slits pattern that's wobbly. But now, for example, we are looking behind the two slits. Then behind the two slits, if we put there an observation instrument, then the interference pattern disappears. And many people are, what happens now? Well, we don't know. Okay, well, it's not so hard. Remember that the instrument is a big mass, let's say 100 grams or 10 grams, I don't know. But that means it's a collection of wave function of atoms, etc. So the wave function of the instrument is a different kind of wave function, in which the wave function of the electron, which has a very spread out wave function, and thus a relatively big wavelength, deBroglie wavelength, interacts with an instrument that has a very small wavelength, a deBroglie wavelength. I mean, each object, no matter what, if you take the mouse, if you take a pen, it doesn't matter, but it has a very small wavelength, a deBroglie wavelength. And the electron wavelength, the big, with a very relative big wavelength, deBroglie wavelength, interacts with something that has an extremely small wavelength because of its mass. Now, it may be very slow or even standing still, although it always wiggles, but it has a very, 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 very small wavelength. And the electron or particle, flying particle, interacts with a very big mass in ratio-wise speaking. So what happens, the wave function of the particle, flying around particle, must decrease because it's interacting, it's entangling in sort of way. And because of that entanglement, the properties of both systems, the instrument, the measuring instrument, suppose that this is a measuring instrument instead of a pen, and the little particle, they become one by a kind of entangling. They start to interact, which is basically some kind of entangling. So, but the wave function of the particle is extremely the particle is extremely light. I mean, the mass of an electron is, if I remember correctly, 9.1 times 10 to the minus 31 kilogram. And the instrument, the measuring instrument, it may be, well, what does a pen weigh? Let's say it's 10 grams, but it's still a huge difference between the two masses. So the wave function of the electron must adapt to the wave function of the measuring instrument, and thus it merges, they merge, so to say. And of course, because of the measuring instrument is way much massive than the electron, basically what happens is that the wave function of the electron shrinks. The deBroglie wavelength of the electron, because of the interaction. If there is no measuring device, nothing happens. Then the wave function of the electron remains the same. But if it interacts by observing, then the electron wave function is forced to change to match the wave function of the measuring device. And since that wave function, that wavelength, the deBroglie wavelength of that instrument is way much smaller, therefore also the spreaded outness of the wave function of the electron shrinks also. So it doesn't collapse, no, it shrinks because of the interaction with an object that has a way much smaller deBroglie wavelength. And that's why the interference pattern disappears. It disappears unless we are able to shrink even our detection systems to very extreme small sizes and masses. In that case, if the weight or the mass of the instrument is if we are able to reduce, and this is a prediction, a scientific prediction, if I'm correct, that if we are able to reduce the instrument measuring device instrument to the size or the wave length, the deBroglie wavelength size of the flying around particle, then we see a less dramatic change of wave function interaction. But suppose that the electron is able to fly beyond the two slits and is not being observed. Then also when it hits the screen, then it also interacts with the detection screen. And of course, again, if this is a screen, then tiny particles is way much smaller than the detection screen. So also then what we call collapsing is happening, although collapsing is not a good description of the process that is happening. It's not collapsing. It is merging with the wave function of the detection screen, and thus the wavelength is also strongly decreasing. So basically that is what's happening. It's not collapsing. No, it is changing to another wave function. And yes, that may happen instantaneously. That's correct. It may happen faster than the speed of light or whatever. But because of that's mathematically required. And so the description of collapsing is not entirely correct. It is the wave functions are merging, and I wrote down here below a formula that the wave function times the mass of the particle plus the wave function times the mass of the detection screen or the instrument divided by the combined mass of the particle and the screen. That is the new wave function of the combined particle screen or instrument thingy. It's new. It's a new object which was added, which in this case an electron or another particle was merged with the detection screen or instrument. And so they go alongside in a new wave function, which has indeed a very, very tiny wavelength, a deBroglie wavelength. So that means that there took place an alteration of wave functions, not a collapse of wave functions. And yeah, the spreaded outness. I mean, if you have a particle that's floating around in space-time, then it has a measure of spreaded outness, and that's what we also see in, for example, the delayed function, the delayed choice thing. Well, that spreaded outness is playing a key role in the way of detecting and interacting, and but also interfering with itself. But as soon as a wave function, if a particle interacts with an instrument, then the wave function must, or the wave function must alter in such a way that the deBroglie wavelength shrinks to incredible small sizes, and thus, for our perspective, it vanishes. So hey, now it's spread out, that wave function, and all of a sudden it shrinks to such an undetectable small size that, for our perspective, it's not visible. And it turns out that it hits on two spots instead of a wave function interference pattern. That wave function interference pattern emerges only if we allow the particle to be spread out in space-time. If we bring the particle in contact with an instrument or with a screen or whatever, a macroscopic object, then the wave function of the particle is forced to merge with that instrument wave function, and thus have the wave function, the deBroglie wave function, has to shrink to for us unmeasurable sizes right now. I mean, maybe in the future, but for now it's unless you make the instrument in the order of magnitude of the same sizes, or in that range as the particle that we are observing. I mean, if you use macromolecular structures as a detector, maybe you can detect it in such a way that the wave function, the deBroglie wavelength, does not change so much in ratio. And thus, this is what I want to share. And yeah, this is a thought that I want to share. And I think I wrote it also in some papers that I already published, this idea. Okay, thanks for watching, and see you next time. I have to be quitting because the internet connection is not that good, so I hope it still works. Okay, thanks for watching. Hasta la basta. See you next time.